Good afternoon, everyone. Can you hear me? Hey, great, great. So everybody is able to hear me. So, did you have a difficulty in understanding the assignments last time? I could not describe you the assignment last time. So, should I should I explain a little bit more about the assignment of the last class? Okay, on session 3. Okay, okay. On session 3 and session 4. Okay. Okay, so some had a problem understanding session 1 and session 2 and session 3. Okay, so with respect to session 2, almost all of you have done great. Okay, A- all of those who have submitted their assignments have done really great. And except for one or two persons who have confused capped collection and cap theorem. Okay, some of us have confused capped collections and cap theorem. That's the only mistake that has been done. Other than that, everybody has done really good, and we are happy. Uh, And with respect to the assignments, let's say some people are saying that there is a confusion on session 3. Okay, so let me just have a look at the assignment 3 of that one. Yeah. So in this one, which part is not clear to you? There was somebody's question saying, I did not understand the this phase. So what is the problem related to this session number 3 assignment? Yes. Okay. Okay. So basically the idea was to, based on the concept which we learned in session number 3, whether to make, okay, so whether to keep a object, such that, what kind of, what all collections will you make in your database. Okay, so as we know that we don't have to define schema per se, but you need to plan that these are the kind of data you are going to store in this collection. These are the kind of data you're going to store in this collection. I'm going to combine all of these objects together, keep it simple. And the other way would, you know, the other kind of design decisions you will have to take, whether to keep another object as a part of, in case of one to many relationship. Say, do you want to keep the many objects of that one relationship as part of this object itself as an array, or you want to keep it separate? Okay, so basically you will have to figure out what all objects are you going to, what all documents are you going to keep in a collection, and what kind of collection is it going to be? Is it going to be a capped collection, normal collection, and what are the indexes you are going to create on that kind of document? Okay. Okay. So Yogesh, did you attend our session 3 class? Okay. Okay. So okay. So basically, there we discussed in the session 3 that say unlike your SQL where you create separate table for each entity and then a separate table for defining relations between the entities, here you do a denormalization. Okay, because the data which goes together, you generally keep that data in a single collection. The data which goes in different I mean, which caters to different needs, will have to go into different collections. So actually, I think because it's a very I mean, it will take a little bit more time. So maybe you can go through the session three's video again once, and then let me know if you have still doubts. I'm very sure that you should be able to do the data modeling if you have gone through the video of session 3. Okay. If in case still you find it difficult, what I'll do is we will have a separate call, where I can re-describe what I had done in the session 3. Okay. Does it make sense? Okay. So let's say that, so let's just build a very simple one. Okay. Called employees data. Okay. Employees and their salaries. Okay. So let's say we have a collection called employees. Okay. And each employee looks like this, what is there in curly braces. There is a name. Okay. There is a employee ID. There is an employee ID. And basically there is, say, date of joining. Okay. Now, now we can have something like departments, okay, as an array here. All right. Because departments is not something which changes frequently. Okay. And so on. Okay. And then we can have again called manager, which is again a ID, basically referring to somebody else's ID object. Okay. So this is one very simple object representing employees. Okay. And here in case of MongoDB, instead of distributing or normalizing data too much, in case of MongoDB we try to keep everything, most of these objects merged together, so that we don't have to query multiple collections at a time. Okay. So see, if department is just a name, say something called like physics. Okay. Physics. And so we can have an array of objects in the departments, not physics, let's call it engineering. and so on. All right. So either what we could have done is we could have created a separate collection called departments. Okay. And then we could have created another collection called department employee relations. Okay. So this is not required in general in case of MongoDB. Okay. When you have one-to-many relationship, you can actually represent it like an array instead of having these kind of two extra collections like RDBMS. So this is a very, very simple example, but I would strongly recommend that you go through the talk again. And in case you have doubts, because there are a lot of some more angles to it. Okay. If there are more doubts, just let me know. I can, explain to you again. All right. Yeah. Great. So we were talking about this one. So here this question is clear to everyone. Is this question clear to everyone? Because I have got only two submissions so far for this question. Okay. So I'm wondering, so somebody was asking me about total number of users may grow to be 100 million. They did not understand that. So is there any way we can restrict updation on DB level? Mm, not really, not really. The only way is to give the permissions on a collection, which we will describe in case of a user and and basically user and administration session on how to create an object and how to create a collection and how to add a user to it. Okay. Okay. So this question is clear to everyone, I'm assuming. I want to take and with respect to session 4, what are the kind of doubts, or should I describe the question completely? Yeah. So most of us could not basically had a difficult time in importing, because this sentence here says that same data has been imported into following database, but this the data was not imported. So some people face the problem, but one of us actually imported the whole data into the test database itself, and is probably available now. Okay, I will check after the class. So basically in this is basically a database. I will show you. Okay. So this database is basically from Enron. So, so after Enron went bankrupt, their email ID corpus was made public because it was a public company. Okay. So after Enron went bankrupt, so the email data was made public, and this is the actual email corpus. Okay, this is the actual email corpus of around 1 year, of around 1 year. Okay, and we have formatted it into the JSON format. This is a 400 MB file. Okay, and okay, so collections db.messages.find1. Okay, so if you say db.messages.find1, right now in the test database itself, it has been copied. Okay, and it is just showing the first message out of the collection. Okay, so it has got a body, it has got an ID. Each email has got an ID. Each email has got a body. Okay, and each email has got something called file names. Okay, in case there is an attachment. So okay, and these are the headers, like who sent mail to who, like the mail came on this date from reservations, and message ID is this, subject is this, and it was sent to these people. It's an array. In this array there is a single element. So basically it's a complete dump of the emails. It's a complete dump of the emails. Right. So Pramod's question is why only, because this user student has been given permission only, not on the uh, Enron database. It was given permission only on these database. We need to look at it, and before basically we will also learn how to give permissions to users and how to create users. Okay, in the on next weekend. Yeah, so that also you can give that kind of permissions to creating a new DB also. Okay, so those permissions are missing. All right, so we'll provide those permissions. Till then, you can continue to use it from the test database itself. Okay, now this file has got show DBs. So how big is this file? Yeah, promotes pr promotes use promote and show DBs. So this so show collections. Okay, so it does have messages in it. Okay, and probably yeah. Okay, all right. So basically this table db.y. Am I going into this? Okay, good. So this one actually shows you the complete detailed email messages. And the questions here were, first was find top 100 people in this organization who sent most emails. Okay. Find top 100 people in this organization who sent the most emails. The listing should be in the descending order of the emails, of the number of emails sent. So basically, you need to apply aggregation. You need to apply aggregation on the from field here. It says that who sent most the email. So we have to just list down all the email ID from email IDs here, and then you will have to run a simple aggregation on this. Okay, so if you say project header.from, you will get from it, and then if you pipeline it further with the uh, top with the order by pipeline, and then followed by limit, then you will get a top 100 people. All right. So this is first question. Second is, list down top 100 pairs in this organization who communicate most with each other. Okay. So you'll have to find out 100 pairs of such people, top 100 pairs who talked to each other most. Okay. So as an example of what I'm expecting as an output, say A sent an email to B and C, then A sent an email to B and D, and then B sent email to A, and B sent email to A and B. Okay. Now out of this total pairs we got is A and B is 1, A and C is 1. Okay, then we have got uh, out of the next one, A and B is 1 again, A and D is 1 again, and then B sent to A one email, B sent to A again one email, B sent to A, B sent to B, which is self, is 1. Okay. So this is to be ignored. This duplication is to be ignored. But let's say that it is there. Okay. Now out of this, I just ordered this list. Okay. So I got how many, and also BA and AB are equivalent. Okay. Because we are trying to find out the pair. So I can simply write this also as a B. All right. All right. So all I'm trying to do is trying to figure out how many conversation happened between A and B. How many happened between A and B now? Quick. So yes. So 4 happened between A and B. Okay. Now between A and C, 1 happened, and A and D, only 1 happened. All right. So out of this list, we want only the top 100 such pairs who communicated most. All right. Is the question clear to everyone? Second one, uh, because there are two catches in this. First one is a person can send email to multiple people, and second is that any conversation from A to B and B to A both has to be summed up together, total. Right? So that is the interesting problem, the second problem. Okay, and you are free to use either of the system. Okay, either you can use either you could use aggregation, or you can use MapReduce, or a combination of the two. All right. And this is very, very important. The only reason we are learning MongoDB is for these reasons, right? So that we are able to query quickly. We are able to answer these kind of questions. The other part, like administering, installing, creating users, giving permissions, are just the the purpose of all those activities is aggregations. So that you can do aggregation, you can churn a lot of data. All right. So try to come up with this. And in case you guys have a difficulty in MapReduce, just shout out now so that I can try to explain again. Okay. Because last time I had to cut it short, and I did not give enough time. So are you guys clear about the map and reduce paradigm? How do you break down any problem into map and reduce? Hmm? I'm putting a question mark so that I can see your answers. So are you clear about what is the map reduce paradigm? Yes. So in the second question, the problem would occur. In the second question, it is very easy to do. First, you take the list and do a unwind so that array becomes key value pair separately. And then basically what you can do is you can sum up all the emails A to B, but the problem after doing all of that would be, you can do a group by creating a composite key of A and B. Okay, so you will get A B 3 and B A some number. Now problem is how do we make sure that A B and B A are considered same, right? So there, for this particular task, what you could do is you could use a map reduce such that map will produce a key called A comma B even if the mail was sent from B to A. Okay. So whether email was sent from B to A or A to B, the key should always be A comma B so that these all numbers can get summed up together. Okay. Does it make sense? Like I gave you example here. So i- if I have to solve this problem using MapReduce, let me just put some more data here. Okay. So C sent email to A, B, and D. All right. Okay. So now what we have to do is we have to basically find out who are the most, who sends emails to each other more. So we break down all things into three columns. So A sent email to B, 1. A sent email to C, 1. Okay. Here the key is A dash C. Okay. You can think about the key as this one. Okay, so Rizwan is saying that there is some, yeah. So tags is there in the similar way, the way I'm explaining right now. It is a similar phenomena. Okay. Now I'll describe you in a very simple words. So this is our emails data. Okay, this is our emails data. A has sent emails to B and C. A has sent email to B and D. B has sent to A. B has sent next email to A and B. And C has sent a fifth email to A, B, and D. All right. Now we have to find out who are who are the people who talk most with each other. Okay. Now you write down like A sent an email to B make it a single key. All right. Single key. We are forming pairs who communicated how many times. So because of this email, A communicated with B once, A communicated with C once. Okay. Now out of the second one, A communicated with B once, A communicated with D once. If we sum up these A, B together, we'll get A communicated with B twice, right? And so on. Similarly, B communicated out because this is because of the first email, this is because of the second email, this is what I'm doing right now is third email, and this is my fourth email. Fourth email is B sent an email to A, all right, once. Alright. Now while forming these key, if I form here also AB instead of saying BA, okay? Now then I'll be able to count these things properly. They both will get summed up. The first one as well as this one. Make sense to you? So because we have to count what all communication has happened together, either we write BA everywhere or we write AB everywhere. Okay, because it's the same thing. A talk to B or B talk to A. Now, in the second one also, we say communication happened between A and B. Okay. Sorry. The communication happened between B and B. Anyway, this is we anyway going to ignore. And fourth one is C, communication happened with A and C, okay? And then communication happened between A and B, one, and A and D, sorry, A and B, not A and B, but B and C, okay? And similarly, the communication happened between D and C and ones, all right? So what I have done is I have broken down each emails into the pairs, okay, such that I have not represented a pair like in two modes. Like I can either a pair can be represented like AB or BA. Instead of keeping as two different keys for a pair, I have just created a single one called AB. Okay. Now if you do a sort over here, you will get all the things together, right? So this job, what I just did manually, converting this into key value pairs. Here my key is a composite key of A and B, and my value is 1. Okay, this is the job to be done by your map function. Okay. Now this map function you will have to write such that it breaks down every email message into a key and a value. Here key is the name of the pair, which is AB, and 1 is my value. So this is the duty of the map function. All right. Now if you say sort is what out of the output, this is the output of the map function you have written. Okay, so map function gave us this output. Now what are we going to do is we are going to sort it. Okay, and who is doing this job of sorting? MongoDB is going to do the sorting for you. Sorting by the on the basis of the key you have just created. All right. So whatever key you create as the result of mapping map function, MongoDB will sort your data on key. And once that is done, it will form an array like it will combine all the values which belong to the same key. Okay, like in this case after sorting it, the next duty is of MongoDB is to combine them together like this. So it will you will get 1 comma 1 comma 1 1 2 3 4. So you will get, okay, MongoDB is going to convert this into an array of values if they belong to the same key. Okay. All right. So this is what it is. Now, these things which have multiple values are going to go to your reducer. Okay. So your reduce function will be executed, and it will get two values as parameter. First one is the key. Our key is a composite key of A and B, and second parameter to your function would be an array of values. Okay. Now it is up to your reduce function what to do with this array of values which are belonging to the same key. Okay. So once that is done, so in your reduce function you will write that sum up all these values. Okay, and it will be 4. Okay, and this will become 2, and the rest will remain as is. So yes, so Rizwan, yes, it gets a reduce function. If you had seen our in the last exercise, the reduce function more or less looked like a here reduce function. If you see, this is it'll get two parameters. First one is key and second is values. Values is an array. Okay. So this parameter is very powerful because you did not have to intervene or did not have to manually distribute the data. All you had to write is map and reduce. Yes, Rizwan, it will always be an array. Okay. So here you only thing you did was you took an array and did a basically did a summation. All right. You could do an average, you could do a standard deviation, you can do a mean or whatever you wish to do. You can do it in your reduce function. So how to convert this array into a single value is the duty of your reduce function. Okay. So is that clear now? I'm sure you will be able to solve the second question now. But do it by yourself. Why I'm emphasizing a lot on this paradigm is because this paradigm is sort of universal. Whether you are using Hadoop, you are using Spark, you are using any other framework, even CouchDB, everyone has everyone has a I mean similar kind of paradigm of MapReduce. All right. In case you have any doubt, just try to ping me and then I'll answer. Okay. Make sense? Now the third question is list down top 200 keywords using uh, to top 200 keywords used in this organization, which are not a, an, or the. Think about the last question and think about all the various approaches you can come up with, whether aggregation, whether map reduce, or any other technique you can come up with. Okay? Or a combination of the two. Clear the questions of fourth session and third session are clear to you guys? Great, great. Now, okay. So this is what was our MapReduce example. So MapReduce is a very important, and I mean, it might look that why are not we querying and why are we using MapReduce when everything can be done through querying? The problem is that it is not possible to prove that everything can be done by aggregations or querying. There are a lot of things left, such as I mean, there are a lot of functions which are not yet there in the aggregations. Okay. And in case you have to do that kind of thing, you might have to end up with MapReduce. Okay. Because MapReduce gives you, yes, you can't do that in SQL Server actually. SQL Server, you'll have to write PL/SQL and churning, imagine doing this in SQL Server exactly. And if you have got say 200 GB of data and you are running it on a single machine, that machine will not be able to give you the response. Okay. Here, when you run the map reduce, the map and reduces are distributed all across the cluster, and all the machines are performing your task in parallel. You're right. Great. Great. Okay. Great. So now let's move on. So this we have done. So aggregations assignment, please submit because I have only got two answers yet. I need to get, and your the previous assignment have been reviewed. The session two's assignment have been reviewed, and out of that, the capped collection and capped theorem was one confusion some people had. And please review the comments given to you by the TA. Okay, and see if you can, if you have any doubts, just let us know. Okay. I'm also reviewing parallelly as Samta is reviewing. Samta is the TA for the batch. And okay, so I'm also reviewing parallelly. And basically, I mean, you guys are doing a pretty decent job actually. Okay, now, okay. So indexes we have already talked a bit. Just give me a minute. Just give me a minute. I'll have to mute you for a second. Yeah. So I'm doing a little bit recap of indexes also. Indexes are like analogous to your actual indexes. Basically prepares a list of sorted unique values of that particular field in your document. And basically these are special data structure, mostly B trees or B plus trees. But in case of MongoDB, it is B trees. And indexes are created at collection level. Each collection will have their indexes, right? Each collection will have multiple indexes, and you can also create various kinds of indexes. I will go ahead and describe you. And in absence of index, MongoDB scans each document, okay, used by math sort and projections. Okay, so in if there is no index present on a document, and you say query this on that, then MongoDB will actually go through each and every document, comparing your aggregation conditions or any other kind of find parameters. So it will go through each and every document, compare your condition against the document fields, and then decide. So this methodology is called, when it goes from one end to another, reading one document at a time and comparing instead of jumping directly to what you're looking for. This methodology is called scanning from one end to another. Okay. So in case of if you have been acquainted with databases, so in database we call it read scan or other kind of scans. and we try to avoid the scans as much as we can. Okay, so this is basically, indexes are basically used by any match or sorting operation. And note this sort keyword. Basically, when you say order by, then also indexes are used. So indexes are not only used, I'm sorry, I'm so sorry. Okay. So indexes are basically used by match as well as sort operations. Okay. Whenever you are ordering the data, then also the sort is being used. And also in case of a projections, if you are using a projections and all the fields in the output are basically covered. So anything you are projecting in the output, if there are indexes on each of the fields, in those cases, the indexes are useful for the projections also. Okay, and this kind of circumstance where everything which is there in projection is select a comma b from my table. So a comma b is my projection. Basically this is what I'm trying to select. In case a comma b are both having indexes, there are indexes on both of these fields. In those cases, this kind of query is called covered query. Okay, covered by indexes. And in these kind of queries, you do not, you do not scan the table. Instead, you use the indexes. Internally, the database will use the indexes for you. Okay. So this is what an index is about. And this question I had asked you a little early also. So say you have got 1 billion records. Okay. You have got 1 billion records in a collection, and there are no indexes on a particular field. So what you do is you're looking for something, you pick up one object and compare it with the value you are looking for. That comparison is taking around 1 millisecond. All right. Now, this total comparison of billions of record is taking around 12 days. Now, after index, how much time same comparison will take? So you have got a big collection which has got 1 billion records. You are looking for a document, and to find a document, say a name equals, say Umang. So you're looking for that kind of document where name equals Umang, and that comparison is taking around 1 milliseconds. Okay, and the total comparisons one by one is taking around 12 days. Okay. Now you have to tell that in case we index this table on that column called name, or if we index this collection on the field called name, what is the approximate time it will take to query for Umang in this collection? Anybody quickly? Give a rough estimate. 3 to 4 seconds, yeah. Anybody else? Less than 10 seconds. Okay. Okay. So it takes around 30 milliseconds. All right. It takes around 30 milliseconds. Because if there are 1 billion records and it is taking 12 days, okay. So if you convert that into a number and say, see that this is how much time it takes to compare a single document, and then do a logarithm of 1 billion, which is 6 milliseconds, 9. Okay. And you will get a number around 30 milliseconds. Okay, because 12 days is how many milliseconds actually? So we have got 12 days, 12 into 24 into 60 into 60. These many seconds divided by 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, that is our 1 billion, and which means 1 milliseconds, right? So each document is being compared within, say, 1 milliseconds, right? So these two, one of the information here is redundant, okay? And so when it's taking 1 million millisecond to compare a record, and you have 1 billion records, so approximately 9 into uh, 9 into log of n, okay? So approximately this is what 28.5 millisecond is what it is going to take, because there will be how many comparisons? Total number of um, total number of n log n comparisons. Okay, basically log n comparisons would be there, so it will be even further faster than 30 milliseconds. Okay, yeah, log of n is basically 30. Log of 10 to the power 9 is actually 30. All right, so it is going to take log of n time. So does it make sense? No. Wahid Rizwan, does it make sense? No. Okay. So okay, okay, okay. So basically, whenever we do an index lookup, there is a binary search that happens. Okay. So if you have 100 records, okay, if you have, say, if you have, you remember binary search, we discussed that we jump between the two. Okay, you jump between the two. Now, if you have, say, 4 records, how many comparisons will there be in total? Maximum comparison possible. So we'll jump somewhere in between. So one comparison will wipe out half, then another will comparison will wipe out the rest of two. So if you do a little bit of mathematics, you will find out, you will do a comparison of log n. If you have n numbers, n total numbers, okay. If you have n total numbers of records, okay, so every so total number of comparison which will happen to find out a particular record in n records, if they are ordered, is log base 2. This is log base 2. Yeah. Okay. This is log base 2. Meaning, so say, let's say that there are total number of x comparison possible, right? And every time in x comparison, we are eliminating how much? We are eliminating uh, half of it, right? So at every step, it is becoming, at every step, it is becoming half. Okay. So 2 to the power x will become equal to n. So every comparison reduces the total record set into half. And if there are x number of comparisons, we have actually covered up all n records. Okay. So if you do a little bit of maths, you will find out that if there are x number of jumping happened, we will cover all n records, and thereby, so how should I describe it? So let's say that you have got 4 records. Okay. So you will reach to the result in how many comparisons? 2 comparisons. Okay. If you have got 8 records, you will reach to the record you are looking for in three comparisons. You jumped into middle, divided the whole set into whole 8 gets divided into 4 and 4, and then that 4 will get divided further into 2 comma 2 two sets, and 2 will get divided further into your result. Okay. So this way you always, so here there are 3 comparisons: first one, second one, and third one. Okay. So 2 to the power whatever small n. Okay, if there are total number of n steps, will cover capital a total number of records. Okay, and here when you do a computation, n equals, it becomes log of capital N, and where log is on base 2. Okay, so this you agree, right? This you agree. 2 to the power small n is like total number of comparisons you have done. Okay, is equal to the total number of records. Does it make sense, Wahid? No. Okay. So similarly, and therefore, in the similar way, if we have how many records here? 1 billion, right? So ln of 1 billion is 10 to the power 9, right? Which is equal to 9 into ln of 10. Okay. Let me open the calculator. Okay. ln, when I say log, there is a log base 2. So I'm saying log base 2 into 9. All right. This is how much? 29.89. Okay. Which is 30. 30 milliseconds we are talking about. Make sense? So basically what I'm trying to say is that when you are jumping into halves and halves, and every time you're jumping so far, into the document in the middle of it, you are all the time discarding half of the document. Okay. And this way it becomes lightning fast to locate a number. Okay. And it is also possible to prove that jumping halfway is the most optimum solution rather than jumping into 3 parts. Let's say we divide the whole n records into n by 3, n by 3, n by 3. Okay. So it is possible to also demonstrate that jumping in between is also the one of the ways. So this is basically all of this what we have just talked about, called binary search. Okay. And it is, if you are really interested in binary search, you should go and actually look at how binary search works. Okay. Because that is the mother of most of the algorithms all around you will use. Okay. And binary search can be used in millions of ways in your normal developer life. Okay. Or in a normal, say, you messed up your code. Okay. You are deploying a release. Okay. So say you are deploying a release to the customer, and customer says that we have got a bug here. Now you don't know that which change particularly has broken your release. Okay, which change particularly have broken your release, and you have done say hundreds of release in last 1 week. This particular customer who got the 100th release is basically cribbing that we have got bug here. Now you being the development manager, or you being the developer, or you being the person in charge of deployments, your duty is to figure out which particular release broke at the customer end. So what you do is, quickly, whatever uh, code base you use, you check out on the day one and check whether the release is working or not. Okay. Then you check on 100th day, which is say today. Okay. Is release working or not? if it is working, say it was working here and it is not working here. So what you do is you jump in between to 50th day. Okay. Now next is your 50th day. All right. And then you check out the code on the 50th day and try to see if that bug is there or not. Okay. Now, if you say that there could be two scenarios here. There could be yes, ठीक है? There could be two scenarios. One is yes and other is no. Okay. In case you got a yes here, okay, in case you got a yes, release is working at the 50th, then you jump at between 1 and 50, sorry, 50 and 100, which is 75. Okay, because from 1 to 50 it is working, so you will jump at 75. And if the release was not working on the 50th code check-in, okay, if it is not working, then bug could be between 1 to 50, which means next target will be 25. Okay, and this way you can quickly reach to a particular release in how many checkouts, in total number of how many checkouts, 100 and log base 2, which is total number of 7 checkouts. You can find out which release is not working. Now you understand the power of the two, right? Power of the binary search. You had 100 release over, say, 3 months of period. Okay, and suddenly one of the customers says that in my particular environment this is breaking, and you found it that out in 7 checkouts. Okay, so this is a technique which you could use being a manager. Okay, and being a tester also, these binary search techniques works out pretty well when you have a huge data. So I'm basically, what I'm talking just now is general tricks we use in case of a development. All right. So this is and therefore this technique we used to use a lot. This technique which I just described to a binary search in case of in case of code, and therefore tools like Git, they came up with a command called bisect. Okay, which help you doing the same thing quickly. Okay. Similarly, say you are doing a testing, you are doing QA, and in QA you have got say particular your product is breaking at, say, 1 million records. Suddenly on 1 million records is breaking. There also, to figure out exactly on which number it is breaking, or which data set it is breaking. So you keep on reducing your data set into half, or say you have got a great list of uh, input. Okay, and as you kept on increasing your input, the suddenly the data, your product broke, right? To find out exact threshold where is your product breaking, binary search is a very efficient mechanism. Okay, so similarly, so binary search is a general mechanism. That is why I am taking a bit of, I'm going a bit, I'm digressing to explain to you that binary search could be a very effective tool to solve a lot of more problems than you can imagine. Okay, most of this, like release finding, at the prima facie, this whole problem of finding which particular release broke looks like an impossible case to find out. Okay, looks like a very impossible case. But when you do a little bit of maths, you realize that in 7 checkouts I will be able to find out. And 7 checkout is how much? It will take at most 2 hours of my time, even on the complicated product, to do a seven checkout 7 times in sequentially. First checkout, then try that out, then second, then four, and then you can, in 7 checkouts you are able to figure out the problem. So that is the power. But if you look at like a commonsensical way, If you look at the commonsensical way, you will say it will require 100 checkouts, and that's not possible for a team to do it now. Okay, so that's why that's a power of binary search, and there's a power of binary search being utilized in almost every way. Okay, similarly, if you keep on doubling things, right? If you have to generate the biggest text possible for the stress testing and application, you keep on doubling the text size. You control A, control C, control V, control V, and then you keep on doing it over and over, and then see in within fraction of seconds you have 10 GB of text, and over there. So that is the power of doubling or halving. Okay, so remember these things. So the same thing is being used in indexes. Although it's not a straight away binary search, it's a little bit deviation from binary search. Okay, but it is good to have that psychology in place that hey, this is going to do binary search. Therefore, creating an index on a double value, or creating an index on sorry, while searching, if you are using a regular expression, index will not work. So once you have that psychology in place, psychology of index in place, then you will be able to answer quickly whether this kind of query will utilize any index or not. Okay, does it make sense to you? Was I able to explain the binary search and the indexes? Mohan? Sanjeev Mohan? Great, great, great. So there, I mean, all right. So other way to visualize your index is this way. So when you say db.myCollection, which is users in this case, find where score is less than 30. Okay. This is my index. This is my index, the blue one. Okay. Where it's an ordered array which varies from min to max. Okay, from here to there. So whenever we say score less than 30, it is going to quickly jump to 30 and give you these all results. Okay, so using a binary search or b3 or whatever, it will find out this thing quickly, and under this there will be a pointer to the actual record in the collection. Okay, at each of these location the value will be a pointer to the document, or you can think of it as an ID of the document, and using that you'll get the documents. So this is basically an example of index in strictly MongoDB terminology. Here we have got the various things I'm going to talk about today. First one is what are the various kinds of indexes. Various kinds of indexes start with your default underscore ID, then single field, then compound, then multi-key, and then geospatial and hashed, and then plain text. Okay, for the string search. Because we have not touched upon multiple other behaviors of MongoDB, which is text search. All right. Here you have got indexes on the single field. Single field indexes are very obvious one. which is what we have been talking about so far. So we created a single field index. Essentially, under the hood, it is going to create a ordered values, basically like ordered values, and each value having a pointer to the actual document internally. All right. So this is the format where we define like ensure index. We don't say create index, we say db.myCollection called record, say for example in this case, and then say ensure index and field name and then ascending or descending. Okay, this ascending or descending would matter when you are using an index for sorting the data. Because in case every time you require the data, you always want male before female, for example, or you always want say false before true. So all these cases, so in case you always want the data to be ordered in certain way by default, so that should be your default index type order, basically whether -1 or 1. So based on your access pattern of the data, whether you want in or ascending order or descending order, you will create index order of the index, right? Now, to understand, after you have created a index, you can say db.records.find.explain this. So this will give you the query plan of find. Here blank means it will match every record, and explain means it will tell you whether the data has got any key or not. Like for example, so I say db dot messages dot find dot say say explain. Okay, so it shows you that there is a basic cursor on messages here. Okay, so this particular query is basically going to do a scan on this table. Okay, and total number of scanned object which are going to get scanned is these many. Okay, and so on. So and this is the servers which are being used right now, called MongoDB 3. Okay, and we are connected to MongoDB 1. All right. So this is where we say records.find.explain. This gives you a decent amount of information. Okay. Now the next one is the compound one, where we want to. It does show you. If you create an index, say we have got db.messages dot find one, okay, and we create an index, ensure index on certain field. I don't know which one should I create. Should I create on headers dot from and then say one? So it is creating index right now. Okay, so index was created successfully. Now the same one, if you see this one, it is going to, not this one. Okay, I think that process is going on. Okay, db say, what I'm trying to do here is, okay, like this. Okay. Now you can see that it's a B-tree cursor in this case. And it says B-tree cursor is on header.from. All right. B-tree cursor here is on header.from. All right. Because that's what we are using right now in the find command. Does it make sense, Rizwan? So I created an index called on header.from, and when we queried on this particular field called header.from, and then I asked for explaining, it showed me that it is going to query this particular for. No, actually when we say explain, it is actually explaining to you the impact of this query. Whatever query you have written in case of find, explain is explaining what is going to do under the hood. All right. It is going to it is explaining what you have done, because this record does not have any such email ID actually. Okay, it doesn't have any such record ID. I do not see two records anywhere. I don't see any. Oh, index bounds. It says that it is trying to search between this range to this range. And in this case, it is basically searching in for only one record. Because index seek can be between ranges, right? Index seek doesn't need to be only for a single value. So by default, it converts any value you pass in into a range, and then it searches that. Yeah, we can get indexes on all columns. So we say db dot messages dot get indexes, and there you go. So here you can get the indexes. Here there are basically first index is on your key, which is underscore ID. Okay. Basically there are two indexes. This is the first one. Okay. And this is the second one. Here the key is underscore ID, which is single key. Similarly here key is this. And this is the namespace, meaning the collection name. And this is the name of the index which is created. Okay. Make sense? Great. All right. So here we are talking about something called compound index, whereby we create index on multiple fields together. Okay. So if we are very, very sure that we are going to search on two fields together, it makes sense to create indexes on those fields. Right. Yes. Sanjeev's question is, are there indexes created by default, such as in case of primary key? Yes. As you can see on in this particular messages table, there is already an index called underscore ID. So by default, if the ID is not there in your document, the MongoDB will create an ID. So every collection, every document in every collection is going to have underscore ID column, and the collection by default is ordered by that ID. Okay, there is already a by default index is there on that ID. So if you are looking for a particular ID in a particular table, it is pretty fast. It's extremely fast. Okay, because it has got the index on underscore ID by default. Make sense, Sanjeev? Now, so we have got something called compound indexes. In compound index, similar syntax. First column, colon 1 or minus, based on whether you are looking for an index which is ascending or descending. And then second column, colon minus 1, which is like this. Make sense? So if you look at the index, this is how the index will look like under the hood. From minimum to maximum, all the combinations of user ID and score ID will lie on the horizontal axis. And in case you're looking for a value, it will start jumping back and forth in this. Okay. Or it will start looking in the B tree based on the ranges. And there is something called multi-key also. Okay. So when you have multiple keys, okay, if you basically think about arrays. So if you have got arrays and arrays contain the object further, you can create the index on those values. Like here, as you can see, you can create index on array address dot zip. Okay, it is okay. So here basically you can see that there is an object. Okay, object has got user ID as one field, another field is addr. Under that addr field is an array. The addr field, address field, is an array of various addresses. Okay, now in case you are looking for an address, in case you are searching for the particular object which contains a particular zip code, it is wise to create the address on create an index on addr.zip. So which means to say that in the as in this case of let's take user id colon say xyz, and we have got addr, and we have got zip colon 123. Okay, okay, and zip colon 124. Okay, so when we create index on this is basically treated exactly like the index on the objects which have say a field called addr.zip addr colon zip 123, and there's another document in this collection called with the same user ID, and but the difference is in this. Okay, so when we create index on addr.zip, this is interpreted like this. Okay, the the syntax for addr.zip is equivalent in both the cases. In case you have got your you have got, say, your collection in this form, which has got one document of this kind, another with this kind. Okay, like unwind. So it is similar to, you can think of whenever multi-key, whenever we had got an array inside a document, inside a field, in those cases you can create an index on those also. All right, because it is not an exceptional case. It is required quite often. All right. Yeah. So these kind of keys are called multi keys. So basically index the content stored in arrays and automatically determines whether we are indexing an array type or are we trying to index an object, like in the case of two examples I gave. Because syntax for both here also, okay, here and as well as here, at both the places the syntax is going to be my collection dot ensure index. Okay, and I'll say addr dot zip. Okay, in both the cases, in this kind of format as well as this kind of format, the syntax is same, so it will automatically figure out which one it is and accordingly create the indexes. I have again given the same example which I was trying to give. So we have got this and we have got this. Okay, these are the both the things. All right, any questions till now? Similarly, the way we had been creating these indexes were pretty simple actually. These all indexes has been going on there in the database world forever. Okay, but the new one, which is geospatial one, is very new in the domain of databases. None of the other databases started giving the geospatial one in the database itself. What does it mean by geospatial? Basically, if you have a coordinate data, okay, imagine having lot of location data and you are trying to figure out what to look for. Okay, so in case that is the scenario where you have a lot of coordinate data and you are trying to figure out, find the values or find the documents near a point inside a polygon, inside intersections of two polygons. In those scenarios, the life of a developer or life of a uh, you know analyst has been made fairly simpler by providing the various kind of searches like geo near and geo within. Geo near aggregate function gives you the data near a particular point, and geo within gives you the data or the documents within a particular location, within a particular polygon. All right, so basically Basically, geospatial indexes are of two kinds. First one is 2D indexes. These are basically a two-dimensional kind of data. Okay, flat two-dimensional data. While 2D sphere indexes are for Earth-like geometry, like the way Earth is spherical geometry. So 2D sphere indexes are for that. But to be very, very honest, you should not be using 2D indexes anymore. 2D indexes is more or less has been obsoleted. 2D indexes are good only if you are churning the old data with a different kind of location format, because every document has to specify that this is the location field they are having. Only then you will be able to search for a document lying within a particular location. Okay. So if your documents have the data in very older format, then then and only in those scenarios you should be using your 2D index. Otherwise, you will be using your 2D sphere index. Okay. 2D sphere indexes are for computation or finding locations near a point or inside a polygon on a surface like Earth, which is round. Okay. And it does make a difference if the surface is round. So in effect, this is what you should be focusing on, not this anymore. Okay. So basically, once you have lot of such data, it makes a lot of sense to basically keep an index ready so that you are able to quickly find a particular value near a field, near a particular location. Okay. Does anybody want some break for 10 minutes? Should we take a break of 10 minutes? Great, great. Let's come back after 10 minutes. Hi, are you back? Are you guys back? Great. So in the recent releases, the MongoDB have moved to a new format from 2D index to 2D sphere indexes. Yes, yes, we will talk about more detail and we'll give the query example with respect to these very quickly, Rizwan. Don't worry. And so first let me describe you. So when you are trying to, let's just take a problem per se. So you have got lot of data about people. Okay, lot of data about people around the on the map. You have got their locations, where do, and you have got their name and all the information combined together. Now you are trying to figure out that who are the people who exist inside a particular rectangle, or who are the people existing nearby a particular point in a radius of something. So these are the two kind of queries you generally run on the geospatial data. Geospatial meaning geographically. I mean, geospatial is basically referred as the data in the two-dimensional or three-dimensional. Okay, on the space. Now, when you are trying to do these kind of operation, whether finding all the people or the things located in a boundary or a near a point, so you require two things. First, your object should dictate its location. And how can it dictate its location? By putting a value of longitude and latitude in the in its coordinate in some field somewhere in the document. Okay, and what kind of format should it be? That format in case of 2D sphere is GeoJSON. Okay, GeoJSON is a standard format, not specific to MongoDB, but fairly embraced by MongoDB with the with respect to standards. So your object, whichever whatever kind of object it is, it has to tell the coordinates in this format. Okay, in this format. Okay, it has to. So this whole object should be part of your field value. It should say that what kind of coordinate are you specifying? Are you specifying a point or line string or polygon or some other, a combination of all this, composite of all these things? Okay. And then the actual coordinates. Coordinates can be array or can be array of arrays, and so on, right? So in case of a point, you just provided longitude and latitude. Okay. Okay. The the kind of queries does geospatial index provide? Basically, 2D sphere provides you. First is geo within. Okay. When we say geo within, so once you have created these kind of data containing your information, say you have created millions of documents, and each document containing its location in terms of say coordinates. Now the next step is to build an index on it, and afterwards the rest is to how to query it. So right now we're talking about querying it. Okay, so here you say geo within means when you say when you ask a collection, when you ask a collection ki give me all the documents which are in this boundary. Okay, are in this particular boundary, and boundary means a polygon. Polygon is what? uh, Basically a lot of lines joining each other, making a single uh, making a single two-dimensional space. That is a polygon. Okay. Enclosed body where the border is of straight lines. All right. And border can be either a triangle, quadrilateral, and pentagon, hexagon, or any irregular shape. Okay. Any irregular shape having any number of sides. So geo within is one such command or an aggregation which gives you the documents of a collection lying in a particular polygon. Okay, bounded by a GeoJSON geometry. Okay, here if you see GeoJSON geometry, polygon is there, line string is there, and all. So whenever you are defining your geometry, again you will be defining in the query itself in this format. All right. Similarly, we have got something called geo intersect. Okay, select geometries that intersect with GeoJSON geometry. Okay, so when we say geo intersect, we say what we are looking for. We are looking for all the documents in a collection which intersect with our with our geometry. In the previous one, we were looking for all the documents which were lying inside our geometry. Whatever we are looking for, we drew a polygon, we drew a geometry on a particular map, and we are asking the map, give us all the points, all the documents lying inside this border. And the map in this case is our collection. So we are asking our collection to give us the documents which are lying in a particular boundary, or which are intersecting with our boundary. Okay. Second is near. Okay. Near basically returns geospatial objects which are near to a point. When you say near, you basically ask MongoDB to give you all the documents near a particular point within a certain radius. Okay. So it is equivalent to saying find all the points in a circle. All right. Now we have got another one called near sphere. Returns geospatial objects in proximity to a point on a sphere. Okay. So what does it mean? How does it differentiate between near and near sphere? Okay. So when you are on a sphere, because sphere like earth looks flat from our normal computation, but it is not flat, it is round. So in such kind of objects where you are looking for data on such kind of sphere, it makes sense to consider it a sphere rather than a flat surface. Okay. Near is okay for flat surfaces, while near sphere is better in case of a round object, a round basically sphere kind of object like earth. Okay. Now, so as an example of before I move forward, I would like to explain. So if you had tried to think, like, if you are in a position, say one of my friend, the question I gave you in the Twitter, so one of the friend came up with an idea of a Twitter with location. Okay. He said that what I want to do is people should be tweeting messages, people should be tweeting information that this is for sale, this is what I'm looking for, that kind of thing in a particular radius. Okay. In a particular radius, we are looking for that kind of information. Or in a particular radius, we are tweeting. Now, and when people log in, they should be able to see the activity, what is going around them within a kilometer of 2 to 3 kilometers radius. Okay. So he was trying to build this kind of service, and when he came up, when he said that he want to build this kind of service, I asked him like, how is it going to work if your documents are really huge, or your total number of documents are billions? Okay, how will your service scale up? Okay, that's where he said that we need to create some sort of index on top of locations. So we sat down and we said, okay, let's just try to create the zip codes of the world. Okay, we bisected the whole geography into small pieces called zip codes. Okay, and then whenever people were looking for something in a particular location, we'll convert their location into a zip code rectangle and then find it. Okay, it was possible to convert a location into a rectangle very quickly, and it was quite a simple thing to do. So this made the life very easy. This made the life very easy when we are quickly searching for something. But that scheme where we are dividing the whole geography into zip codes is not great. Is not great because we were even indexing our oceans. We were indexing our locations, Antarctica and everywhere where there is no person. So those kind of scheme which we try to cook up by ourselves are generally very inefficient. And then I realized that MongoDB has these kind of things already. Why don't we start using MongoDB for this kind of thing? And so, and MongoDB does a better job than what we were doing. So what it does is it takes the whole 2D information and divides it into this kind of zip codes, unlike our zip codes. So it divides each big rectangle into four pieces, four smaller rectangles, and give them a number. Okay, like here it gave 0 0 1 0 0 1 1 0. Okay, he divided the whole earth into these four pieces, and this one is called 1 0, this one is called 1 1, and so on. Now each of these portions, say this particular one is further broken down into four pieces. Okay, this is further broken down into four pieces. So first one is 1100, second one is because 11 is the one, all of these have a prefix of 1 1, this prefix, and then similar thing is repeated 0 0 1 0 0 1 1 1 after 11. So effectively, if you keep on breaking down the whole map into these smaller parts, you will be able to pinpointedly index each section very logically. Okay, so all the numbers now, if something is starting with 1111, they are closer to each other, and physically also they are closer to each other. The problem occurs when something is on the boundary. Those cases are to be tackled by the system by itself. Okay, so this is the way indexing, the way we talked about indexing on a single line when we were talking about indexing on a simple values. Then for a simple values, we create an index of a single dimension, like a single sorted array of values. Here we split the whole map or whole space into four pieces, and we keep on going. Okay, in case of a single dimensional or single values, we split it the values on single dimension. We split it by only a you say into two each time, right? When we were searching here, when we will be searching, we'll be just quickly jumping into the rectangles and we'll give the output. Okay, does it make sense to you guys? This is called 2D index interval. So basically, this is a very good pattern, and these are also called ND trees. These are a form of ND trees. Okay. So then the next thing which comes in is geo haystack indexes. Geo haystack indexes are optimized for small areas. Okay, these are very, I mean, is only good if you are looking for information in very close buckets. Okay, it's very small buckets. So we talked about what is geospatial with GeoJSON, and then we talked about how is 2D index work internally. And now we're talking about something called GeoHaystack. That's the third sort of thing. GeoHaystack are special type of indexes, okay, for the flat geometry. Instead of using these, ideally you should just focus on 2D sphere, okay, because these ones basically try to create buckets of documents in the same area. Okay. And each bucket contains documents of proximity, all the documents which are nearby, each bucket will contain. And bucket size will dictate how closer documents to be grouped. Okay. So while creating the index itself, you will define the geography, how much distance you are going to look forward to. If you are very sure that the only thing I'm going to look for is within only 1 kilometer, not 2, not 3, you don't want to change that number. In those cases, it is most sensible to create haystack indexes. Okay, but in most of our lives, I mean, these things keep on changing. Now we want to search in 1 kilometer dimension. Tomorrow we might ask user themselves to select in how many kilometers they want to search. In those cases, geo haystack may not work for you. Okay, you might end up using 2D sphere. Okay, this internally uses a command called geosearch, basically as part of the protocol commands, not our JavaScript commands. And this is how you define it. This is basically uses the old traditional way of coordinates, where the position is just defined like this: let long, basically two values, let and long. Okay, and the way we ensure we create indexes, we tell that position is a type of geo haystack, and basically create an index on this places document using this POS field for geo haystack indexes. And type is one means our geo haystack, and 2 and 3 means something else. And then bucket size is our 1 kilometer. Okay, so this is how you define geo haystacks. All right, so this bucket size is of the same radius as you define as your let long is in. Okay, now yeah, in case of let long, I think it is in I think it is in kilometers. This is what I remember. Okay, okay, so 2D sphere are quite important because there has been a lot of research and people have come up with really fast algorithms to search in the location. And because of these kind of properties like 2D sphere, MapReduce, aggregation pipeline, text search, and having objects in place, these are the reasons why people actually use MongoDB. So 2D sphere is one such case which is quite strong over here. So let's take an example here. So we have a document which has got our location, and remember I described a GeoJSON format called point. like like here, type call point coordinates 0 1, and yeah, so we create a document in that format. This location is supposed to be in that particular format. All right, so it can be either of those values. And once you are done with it, what you do next is, this is the same object formatted differently. Okay, here there is a location from type here to here, and then you have got these things. Okay, now when you say ensure index and you say LOC, and this basically this field on which we are trying to create, and the kind of index we are trying to do is this one. Okay, so let's take an example. Right now I'm going to do it in locally. Okay, so db.places.find. Okay, and we can say pretty. So this is what the object has got inserted into the database. And then when we say that, so the object has been created. Now you can use geo within a particular location. Okay, I think I have a running example. Okay, okay, geo within. I have a running example where basically into the, okay. So basically these are the examples. Okay, so it has found that out. Now let me just reformat it for you so that it looks a little pretty. Okay, so when we are saying find the location, okay, so we are saying using our operator called geo within. Okay, and in the geo within, what you do is specify specify the coordinate. Okay, coordinate in terms of, so here like this and like this. All right, now which angle bracket I did miss? Nothing. Yeah, like this. Okay, so I'm saying here find in the places collection where location is within this sphere. All right, and sphere means basically it's not really a sphere, it's a circle. Coordinates of the center and the radius. All right, so find out all the documents which are lying in this radius, in this radius and which are lying in a circle of this center and this radius. Okay, so these are the objects. I can actually say pretty afterwards. Okay, so it has found that in case I say I keep on reducing the radius, then it will not find anything. If you increase the radius to say 3 or say 1 even, still it's not able to find, which means that it is basically I'm trying to increase the radius. Okay, now it has found it. Okay, so basically here where I say geo within, I'm using this kind of format. All right, similarly the other commands like geo near also works on the same principle. And in case you are saying geo within and here you say that array of coordinates, then also you will get a similar results. Okay. All right. So basically, yeah. So I get just a quick demonstration of how does our geo within command work. All right. And importantly, when you are creating, if you do not have index 2D sphere index at all, okay, let's just say db, okay, db dot places dot get indexes. Okay, okay, there is something wrong in this. Mm-hmm, mm-hmm. Anyway, it seems to work, but as per the documentation, it says if you don't create the index, then all the geospatial indexes will not work at all. But here it is working fine. Because if you say find and then say explain, let's see what goes on. If you say explain, it is basically scanning all the objects and then comparing. But if you create an index like this, okay, oh, it already exists in certain database. Oh, not this, I'm sorry. We have to say places or place, I think. Yeah, place. Place is fine, yeah. So it has created that index. Okay, and now if you say again the explained one, now this time it shows you the index bounds. You remember I was explaining you how it is dividing into sections. This is these locations which it has created internally. Okay, these are the bounds of each one. Okay, and here you can see that the lookup now is based on location 2D sphere. All right, does it make sense to you? And also, basically, when you are sharding the data, you cannot use this location as the sharding key, right? I will come back to this again, just make a note of it. What does it mean by not able to use the 2D sphere indexes as shard key? All right. So the other kind of indexes are called hashed. Okay. Maintain entries with hashes of the values. Okay. In certain cases, specifically when you are dividing documents across the network, it sometimes makes sense. It sometimes makes sense to divide data in a completely unpredictable format. Okay. Say you realize that you have got a movie name and you want to divide the data based on movie name because movie name is unique all across your objects. But if you divide the data based on just simply alphabetic order of movie name, you might end up having server which contains THE, the maximum, because almost all movies start with either the or a or some other word. But most of the movies start with THE, the. Now, in case you are saying that, my all these documents, or all these movies are based on the document, based on the movie name is something. Movie name combined with the year is my unique identifier for each document. Now, in case you try to slice it based on alphabetic order, saying AA to AC goes into first server, and AC to AE go into some other server, and so on, you might end up having heavily disbalanced servers. Because as I explained, the all the movies, THE movies, the movies with the start with the, are going to become such a big, are going to take such a big storage, and hence your the whole plan of distributing data goes haywire. Therefore, in such cases like movie name or something which you want to be an ID, in such cases what you do is you create hash of the or that particular key. Okay, and such indexes are called hashed indexes. So before dividing the data across the cluster, what you do is you mark a particular key as hashed, and then use that key for indexing in the for dividing the data in the cluster. Okay, when we will be setting up the clusters, the thought clarity about index will come into place. Okay, so basically the values that are under the hood, going to get ordered, and the binary search tree is going to get created, will not be on the actual value of a field. Instead, it is a more, it's a basically sort of hashed values of a particular column. And again, hashed is a very general word. Hashed is a terminology which has been used in case of passwords for pretty long time. Okay, so basically a basically converting a number or converting a word into another words such that the reversal is not possible is called hashing. You converted another word W2 from W1 using a certain mathematical function such that W1 will always result in W2, but looking at W2 you can never go back to W1. Such functions are called hashed functions. Also, the other property of a hash function is the difference between slightly different keys, say W1 and W2, say W1 and W11, are only very minor differences of single bit, but their hash values will be completely different, very different. Okay, so those are called hash values. The other property of a hash value generally is they are of the fixed length. Okay, so and hashes has got a great value addition. So how many of you know what is MD5 hash or SHA-1 hash, SHA1 hash, or MD5 hash? SHA-1, MD5, either of those. So how many of you have actually been acquainted with the word called hash earlier? Great. Okay, great. So some of us have used and seen it. Basically, converting into, say, Sandeep into, I'll just show you very quickly before getting into. Okay, say I have got a word called Sandeep, and we have got a function right here called MD5 sum. Okay, it has converted Sandeep into this number, and every time I give Sandeep, it will give exactly same number, no matter what. But if I make a slight bit different, say I make it complete capital E, the whole number just changes completely from here to here. Okay. Similarly, in even if the input data is quite huge, okay, in those cases also the size of my hash is same. Okay, the length of the hash is same character. Here is how many characters? It is basically 33 characters. Okay, it's a 33 bit long. All right, so hash functions have got these kind of property. In a similar manner, to make it a little bit of randomized, or to make it little bit of uniform distribution, you might want to hash a particular key such that if we are dividing data on that particular field, the data gets distributed equally. Okay, data gets distributed equally. Therefore, instead of you putting in the hash value of a field by yourself, MongoDB said that I can help you by creating hash kind of indexes. Okay, so it is in effect, convert that particular field into its hash value, and then it stores it somewhere. It stores it in the index, creates the index. So was I able to explain hash? Here I'm trying to create MD5. There are many kind of hashes. You can also devise your own. Say you come up with an idea that you will sum up the ASCII values in the input and then compute the remainder by 32. Okay, so sum all characters ठीक of a particular string name. Okay, say my name, and then you do a percentage by 32. So this is also a decent way of doing it. Okay, sum of all characters ASCII value. Okay, so basically you can create your own kind of indexes also, but it is better to use the standard cryptographically secure functions for MD5 for these kind of checksums or any kind of hash functions. So MongoDB provided their own hash functions so that you can divide the document across the network without any hassle. Okay, is it clear? Is hashed clear? Anybody having confusion with respect to what is hashed? Great. So everybody is clear about what is hashed function. Okay. So Rizwan has got a good question. How does it help in distribution in sharding? So as I explained that, let's say you have got a field, you have got a movie. This is your movies collection. This is your movies collection, and it has got a field called movie name. Okay. This movie name. Now you decide that since movie name is the one which we are going to use it for our distribution. So while configuring, when you're configuring your cluster, you tell your shard sh to create distributed. Okay, I'm just basically, you can say shard my collection, okay, on the basis of name. All right. Now what will it do is it will try to divide the data based on the name field. Now as I said, most of the name field are not really uniformly distributed alphabetically. They tend to accumulate a lot in itself. So all those servers catering to the name, because MongoDB at the end of it need to divide some documents to A server, B server, C server, D server. And how does this division work is by you defining your key of the collection. Okay, based on that key, it tries to divide it. All right, based on the range of a key. So it ranges from here to here. So I can divide it into 10 parts if we do this point to this point on the first server, this point to this point in second server, and so on. Now, lot of data will have a tendency to accumulate together in most of the human languages. For example, there are lots of words starting with alphabet S, while there are only few words starting with Z, X, and Q, and so on. So there is a huge disparity with respect to the alphabets in case of English language. Therefore, it makes sense to come up with another scheme of dividing the data. And the most safe one is the hashed one. Because as I said that if you take a word and you're computing the hashed value of it, is actually making it irreversible. And hence there is no predictable behavior from the input to output. And therefore, it will make a lot of sense to have that as a shard key for the distribution of the rows. Okay. So hash basically gives you a fairly uniform distribution. Okay, uniform distribution as in um, it it will start if you try to count all the output of the hash function. Okay, over a significantly huge data, it will have a equal distribution of whether it is starting with 0 to f. Okay, it will start it will have equal words, it will have equal number of words starting with each character. Okay, so that is the value of a hash function, right? If you have two movies with the same name, then also it is fine as long as you don't use that as an id. Okay, index can, because a word can exist at multiple places in your book. Similarly, index multiple values can exist, same value can exist in multiple documents. Okay, so it won't be much of a problem. If two movies are having same name, they will result in the same hash code, and hence they will end up on the same machine. Make sense, Wahid? All right, so this was about hashed. Okay, these are the few things which you might forget, but still once you look it up again, you will be able to quickly figure out what does it mean. All right, now the next one is creating indexes on text. This is like very important aspect. Giving indexes on text was a rare idea. In the beginning, even MS SQL did not give us the power of indexing. And still, as of today also, their indexing on the text is actually very rudimentary. So in my previous firm, when I was building a document management system, I ended up, because I was using MS SQL for my storage of the documents, I ended up creating my own document search kind of mechanism. Okay, and so I ended up with a basically a Lucene parallelly as well as MS SQL. Now most of my metadata was lying in the MS SQL, while my local system which was indexing the text was using Lucene. Now my metadata, a lot of information was lying in the database, and my text search was happening on the using Lucene. Basically, all I'm trying to say is my data or the metadata or the indexes are in two places now. One is in MS SQL and other was in Lucene. Now, when I tried to join these things together, it became very difficult to join these things together. And therefore I ended up creating my own programming language, SQL kind of language, so that it internally divides the queries into MS SQL and Lucene and then merges them back. Still it was very inefficient. So so that time we looked at the whole way MongoDB provides the text search, and we said that this is probably the best way to do things. Okay, your data is there as well as your indexes are really good, and text search actually is more difficult than you can imagine. Okay, it starts with simple nice string, then it goes on to the things like what if there is a dot, what if there is exclamation and there is no space, and then what if there is a question mark which should not be combined with a word, and then uh, S or ES. Okay, when you look for donkey in the text, it should match with the donkeys also. Or if you're looking for INDEX, index, it should also match to a fairly good amount with indices, right? Similarly, in case you are looking for say play, 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 now it should also match with PLAYING, playing, PLAYES, and so on. So this kind of extension to a main word is called stemming. So these kind of properties are being provided very well by MongoDB. Okay, stemming algorithms, and then removing the special characters, and also multiple languages are being supported by MongoDB. All right. So this is what it is. So in the reviews, if you see, I say that again, this is actually causing me a problem. The double quotes are being converted by itself. I'm so sorry. Okay, db.reviews.find. Okay, this is my object. And when I say that create an index on a field called comments, okay, it will take out the text from this field and create an index, right? And in other thing is I talked about something called using special character dot at the end of line, and uh, stemming parts, and there is also MongoDB also takes care of these stop words are common words, a and the and those kind of words, and it will simply cleanly remove those kind of words from the query. Let's look at this. Okay, so I'm saying find using text indexes, using text operator, and search for A. Okay, no, this is the error is because of the quotes. Okay, nothing comes out. But if you say nice, okay, it should give you something. It was able to find, right? So lot of heavy lifting with respect to the common words. It is doing it for you. Okay. And these all features can be turned on or off. And here also, again, if you see, I looked for things, not thing, and it is still matched, right? So these are the good parts of using basically a text search. And you can tune all of this so that, and they also work in multiple language. Now Rizwan's question is how to search for common words. Okay, that is not a part of the text search per se. Okay, that's not a part of text search. Okay, you will have to come up with your own mechanisms to first define a list of common words. If you look at MongoDB, it gives out a list of common words as per the manual. Okay, but but what you can do is you can basically do a frequency analysis of any of the large text from multiple sources, and you will get a common words easily. Or say you pick up the Wikipedia and do the quick frequency analysis on cluster, and you will get this output. Yeah, text here is the keyword. Text here is the keyword. I'm saying create index on this collection called reviews on a field called comments of the type text. Earlier, the way we said 2D sphere, and before that we said 2D index. Similarly, we are saying text. All right. Had it been like simply we are doing a string kind of thing, like had it been a number, we could have said -1 or +1. Okay. But in other cases, you have to specify this keyword. All right. Now there are a few interesting things, few more interesting things on top of indexes. One is called TTL. TTL means the document will disappear after a period of time. Okay. These are very useful in case you are doing a processing you have got temporary data which has to be deleted after few hours. Okay. And also this can be very useful in certain time driven kind of triggers for doing all of this. Okay. So whenever you're creating a TTL, you do these kind of steps. So first of all, you say ensure index on your collection, and then say my date on which this guy has to rely for noting down the created time is my this column. Okay. Okay, this is my column name. And then the second parameter which you need to provide is how after how much time the documents need to be deleted. Okay. Now let's have a look at the first example. Let's say we have got this kind of data. Okay, we created index. Index can be created later also. Okay, and the beginning also, even before the data is created. Now we have got a data which contain this information, like created at this just now. New date means just now it is being created, and it got inserted. So log underscore events dot find. Okay, it gives you this data right now, but we have said that this need to be deleted after how much time? After 5 seconds. So approximately 5 seconds plus some more time, it will be able to delete it. Okay, it will be able to delete it, maybe say 10-15 seconds, because it runs in the batches. So it is still showing the results. Okay. All right. Now after 10-15 seconds, it will delete the data. Okay. So general cycle is 1 minute minimum, and then it should be able to delete. Now it has deleted the data. Okay. So basically TTL is one such case where you want your data to be deleted after some time. This is good for using a transient data. Okay. This is good for running a transient data. Or also, if you're creating your own kind of cache, then you can use this kind of index also. a cache which needs to be expired after some time. Those kind of things can be simply achieved using this. And also this field, created date field, need to be of date type when the data inside this, otherwise it will not be able to say. And in case the field contains an array, then it will pick up the lowest value out of that one and delete based on that. Okay. And expiry task runs every 1 minute. Okay. So even if we say 5 minutes or 10 seconds, 5 seconds or 10 seconds, it will still get deleted after 1 minute. Is there any option for auto update? What does it mean by auto update? You mean to say that after that time, it should automatically get updated instead of deleted? No, that option is not there. That option is not there. For that, you might have to write your own, maybe own code to do that. Maybe that is not a common requirement. That is why they have not provided a function. The other property, this was the first property of the indexes, was that you can make a TTL property true. Okay, you can make a TTL property true, and then the document will get deleted after that time. The other property of an index you can utilize is unique. Okay, in this case, as somebody were also asking that all the values need to be unique, and I said no, right? So I said yes, that it is possible to have non-unique value in a field, right? So in case that is your requirement, you want in a field that these values need to be unique, then instead of defining a unique constraint the way we used to do traditionally, we create an index. Okay, so it is sort of that whole feature of unique constraint have been moved to indexes. So you create an index on that field and say this is my unique field, and the moment you try to insert another document with the same value, it will give you an error. Okay. All right. So now this is the syntax of the unique index, right? Now I'll like to show you right away. Okay. Let's say we have a accounts table. Okay. And on accounts table, we are creating an index. We created an index, say accounts, and said tax ID equals 1, and then we said unique equals true. Now, so any value in the text ID is supposed to be unique. If you try to insert duplicate values into text ID, duplicate documents containing the same ID, then that will get deleted. All right. Now let's say what is there. Nothing is there right now. We start adding the document. We added the first one. We added the second one. Now if you see, now we have got two documents. Till now we are very happy. Now the moment we say this, it gives an error. Okay, it gives an error. It says duplicate key exists because we are trying to insert text ID again. So this is a good way to put the constraint on your collection. Now, because of this unique index, what also happens is that two empty fields are also considered equal. Okay, two empty fields are also considered equal. If that field is missing for a document, if there are two fields which don't have that field at all on which you created this unique index, you will not be able to add those documents into the system. For example, okay, for example, let's say I'm inserting a new document. Say it doesn't have text ID field. Okay, let's say I'm inserting one X with doesn't have text ID. Great. Now I'm inserting another document. Now it is giving me an error. Okay, it is giving me an error saying ki you are trying to insert duplicate document, while text ID does not exist in both the things, which means text ID null is being considered equal with each other. Okay, now in case that is your requirement, you want unique constraint, but you also want all the documents without that field to be inserted without any problems. In those cases, you will have to create sparse index. Okay, you'll have to create something called sparse index. Does it make sense? I'll talk about sparse again. Now you look at some more. There are some more exceptions. In case of this kind of format where there is a field called A, it has got an array, and this array has got two different objects. First one, second one. Both these objects have got same value of B. So A dot B is same. Okay. And in this case, if you see, basically we are inserting a single object with two different value for A dot B, right? If you remember the way we were creating indexes, if we say create index on A dot B, it will create index on this one. But if you mark that unique, it will not complain about this duplicacy because this is a part of single document. Okay, so this is sort of a hacky point which I'm trying to make. Okay, in case you are creating an index A dot B on this collection and marking it as unique, it will allow this kind of duplicacy where same document has two fields on the same A dot B and they have a same value. Okay, so that's a little tricky point of a unique index. So sparse index is one that will help us solve that problem where our field is missing on which we created the unique index. Okay, so in this case you simply mark it sparse equal to true, and wherever your field on which your in the unique index has been created, okay, will be skipped from being indexed. Okay, so if you mark it sparse equal to true, like in the above one, or let's take this one itself, or yeah, so let's say we mark it, we say unique equals to true, and also sparse equals to true. Okay, index with the name already exists. Okay, okay, I need to drop the index and then create it again. Drop the index, okay, and ensure index. Now, so you can see that it is there. Now, if you try to insert another object without text ID, okay, it should not give me any problem. Insert name, say x1, okay. You can keep on creating without the text ID. It will not complain the way it was complaining earlier. So basically, the moment you say mark it sparse, then these three documents which do not have our unique index part will be ignored completely. These three documents will be ignored from indexed. Yes, for sparse we need to have in unique to be created. I doubt that. Okay, I doubt that. Okay, you don't need unique for that. Sparse is also basically, sparse will help you not indexing those documents which don't have that field. Okay, so sparse does not require a unique index to be there. It is just I'm basically the whole sparse thing was created just to cater these kind of utilities. Okay, but there are multiple other use cases of sparse without the unique also. Okay, so basically sparse says that when the field does not exist in the document, do not add that as null into the index. Okay, don't add that document at all into the index. That is what sparse says. Make sense, Pramod? Okay, so for sparse we need unique again. That is your question, right? So I'm saying no, it's not required. Sparse in itself is a property of an index which says that in case that field does not exist on which you have created index, don't add the document at all, otherwise it will add it as null. Okay, and therefore in case your index also has another property called unique, it will cause troubles over there. Make sense? Chalo, we need to move ahead now. So here most of it I have already covered. Here this is done. Okay, this is one example I would like to give you more about. So sparse equals to unique plus ignore nulls. Yes. No. No. Sparse means ignore nulls. That's it. Unique plus sparse means uh, unique and still ignoring the nulls. Now I'll show you some more example of how to use sparse. So you have got a table called say scores. Okay. On which we are creating index on score. Okay. And sparse equals to true. Now the next step we are going to do is this. Okay, well, let's take it up. Scores table we have taken, added into scores, db.scores.find. Do we have anything? No, not yet. Scores, no, not yet. Great. Now we are inserting user ID as newbie into this. Okay. Now it is being saved properly. Okay. If you, and we added two more records into it. Effectively, we have an index on score here and here, but there is no index. Basically, this document is not included in our index, right? By virtue of sparse equals to true. So this document does not exist in our collection, in our index. Now, in case we look for score only, so when you say condition score equals this, right? Okay, so here, yeah, so that's not a problem. Let me add it again. It won't complain at all. Okay, so to clear that confusion about uniqueness, I am adding this record again. Okay, it is added successfully, and if you say scores dot find, you will see these four records: 82, 90, 82, and nothing. Okay, now at this moment, if you look for, if you try to sort this data, try to get the data, okay, based on a listing, based on sorted field, okay, called score. Now when we say find me the records, but sort those things based on my score, and MongoDB tries to see if this particular field is having a index. If it has an index, it will prefer that one. Okay, it will prefer that one, and therefore, and also note the hint part. Hint part basically enforces, it forces MongoDB to use the index. Okay, so if we are saying that while using this index which we created, this one will not be listed. I'm trying to prove that in case the field is missing, a particular document is not being added into the index at all. So let's have a look at this. So scores.find.sort unexpected token. We will try again. So which one is giving problem? This is fine. And when I say sort, and maybe I'll basically take it and type it again. Actually, this PDF actually troubles a bit. Okay. Okay. So basically it was just this PDF problem. Maybe here again you'll have, yeah. So if you see that till the point I did not hint, okay. Now I'm saying that use my index, and therefore it is, it has used the index, and hence the record which did not have that value called score had just disappeared, right? Why? Because that index does not have the particular code document, because it's a sparse by virtue of the marking it as a sparse index. Okay, so when we forced MongoDB to use our index, because by default the moment it senses that this field has got a sparse index, sorting will not sorting will not honor sorting will not honor the index, because it has understood that this kind of problems might arise. Okay, now just to prove my point that those documents are being ignored completely from the index, therefore I'm forcing MongoDB to use my index instead. Okay, and hence the whole document has disappeared, right? Now in this also if you say find a score less than 90, these two documents have come into picture, but the null has not, right? But this one does, actually this one does. If you see explain, it will use the index. See, it is using the score index on this. Okay, this document is using actually the index. All right, and therefore this also did not list our document which does not have a score field. Okay, if we have index on score and we added index without sparse, then first record will come in the list when we used hint. Yes, yes, you try that out, it should work out the way you are expecting it to be. Okay, if I find record without index, then what will be the output? Yeah, in case you find the record without index, then all the records will be there. No, in this case, since that value is not matching, okay, value is not matching because null is I don't know if null is considered as less than 90. Okay, let's say that we are creating an index. Okay, we are basically dropping the index from the table and ensure index true. I'm just trying to drop that index. Okay, I'm dropping the index. Good. And now creating index on that table without sparse. Not okay. Here, if you see, I say ensure index. Okay. Now it is created. The next step is to basically try finding it. Okay. This time also it did not give the null value anyway. Okay, which means that null is not lying in this condition at all right? Does it make sense, Vahid? Okay, so you mean to say if we do not have a index on this and then we say this, then also the result will be same, because then the scan will happen. Okay, then the scan will happen, and but the condition checking will be the same. So it is not using any index, but condition checking is happening, right? Okay, so I have explained here again the same thing. If you are trying to create, you want to have a document without a field on which the unique index has been created, in those cases that is the second use case of our index. Okay, and here is a similar thing which I have demonstrated already on text indexes. You should try to experiment on this one little bit. Other than the fields like text, search, and all these fields, there are things like score, and these things also, all the fields also available over there. All right. Okay. Now, geospatial indexes, I have given the same example earlier also. We inserted two places into the places document, and then we did search on that. And 2D index is something which we have not touched yet. So let's say we have got a, a document in this format. 2D index, the format looks far more simplified as opposed to our 2D sphere. 2D sphere, the location looks like this, type equals point and all. Here that is not the case. Here location is simply let long tuple. All right, so if we have a similar kind of thing in a 2D index, so db.places dot find, and also on the MongoDB command prompt, if you press tab, it should auto complete most of the commands, in case you don't know. And control K means deleting everything after cursor, and control U means deleting everything before cursor. So try these: control K, okay, control U, okay. Control K means after cursor, control U means before cursor, and if you press control plus R, you will be able to reverse search in the history of MongoDB. Okay, like this. Okay, so you can quickly search in the history, and if you at any moment if you're searching, you press escape or say control C. Okay, you should get back. This time it's not working. Okay, yeah, so you can also add it before executing. So use these commands: Control K, Control U, Control R. Okay, these things will help you immensely while doing a lot of querying. So let me just see if db.places, let me complete, yeah, so auto complete it quickly, and I've got this. All right, so it is added, and again I'm adding some more values to it. Okay, oh, this is not taken. Now db.places.2d.find, now one of them will be empty, yeah, second one is empty. So I can say, if I have to delete this particular one, if I have to delete this particular one, I can say db.places 2d dot delete. It's delete, right? It is delete, right? I think it is delete. Oh, it's remove, right? Oh, I completely forgot. db.places. Thank you. Thank you, Wahid. Maybe I'm tired now. Okay, so we have got two documents. So in case we do a ensure index on the location, okay, db.places2d.find, okay, and we say, and to see what all indexes have been created, we can simply say get indexes, okay, and this is what you get. It shows you that there is a 2D index on this. Okay, now here you can use the same syntax as you used earlier for GeoWithin, even if the index has been created on 2D index. Okay, so let me just quickly format it. I doubt if it will work. Oh, it worked. Yeah. So basically you can search for these kind of documents. Okay, and I say 40. Nothing resulted this time. Okay, this is interesting. I'm trying to reach to a point where I can only find, I think there will be some example. All right, so that's a kind of i- this example is what shows you the how to search with, basically the syntax is same. Here I'm saying search GeoWithin in this box. Okay, so syntax for searching is same for 2D as well as 2D sphere. Okay, and now let's have a look at haystack. So haystack is, as we told earlier, is basically for a fixed distances. db.haystack.find, and we have got this. And if we say create a geo haystack kind of data, so we have got haystack dot get indexes. Okay, so we have created one more index on one index called on position. Okay, geo haystack, which you can search using this. Okay, here the distance bucket size we have predefined. Okay, and the maximum distance you're going to use is basically should be uh, I mean should be within each bucket. Okay, okay, here this is wrong. Okay, so here you use a geo search, and basically, Okay. Yeah. So to search inside haystack, you always use a command called geo search, and then you utilize the property of a haystack. But remember, haystack is great only in the cases where you are trying to look up only smaller distances around a point. So here we are saying near this point, maximum distance is these many meters. Okay. Or maybe kilometers. I need to check that part. Okay. So run command is not expecting it to be. Okay. For some reason this is not working. Oh, db.run command haystack. Okay. Okay. I think they have stopped uh, trying that out. I'll check with this version. Probably this command is not working in this version. Probably that they have deprecated haystack completely. So we will discuss a bit of haystack in the next session. Okay. And we will try out, we'll also check why this particular command is not working now in this latest edition. Okay. It says that it command does not exist. It was working perfectly fine in the all the editions so far. All right. So we have, okay. So we have completed till hands-on today. And there also we have not been able to complete the haystack. So I will take up the haystack from next session onwards. Okay. Do not worry about this session. This half of the session, I'll have to take it up again in the next session. Okay. Which is tomorrow. We will complete the rest of remaining part of today's. All right. Okay. So all of you, please finish your assignment from session 3 and session 4, and and also also if you have time, then you should at least follow or like our LinkedIn page. Okay. You should click on the like button there on the LinkedIn page, and right. So okay. No, Pramod, your assignment has been reviewed. Okay. Everybody's assignment has been reviewed. Maybe you are not added and also while submitting your subjective questions, first first create a fresh document on Google Docs. Okay, whether from personal account or office account, whatever. Create a fresh Google Docs account, make it, anybody with link should be able to comment. All right. No, your actually your session two's session 2 has been reviewed thoroughly. Okay, it is just the result are not declared to anybody. In case there is a comment, we have put that comment in place for one or two persons. Okay, otherwise all the assignment from session 2 have been reviewed very well. Okay, and all of you have done pretty well except for few who has confused cap theorem and capped collection. Okay. So see you tomorrow, 1:30. Thank you very much. And yeah, okay, great. We will continue from here from tomorrow again. Okay. Thank you very much. Bye bye. Bye Sanjeev. Bye Sanjeev Puttu. And have a great time.